Hi, Stu Schwartz from MasterMathMentor.com. This is video BC14. The topic is velocity and acceleration of vector functions. It covers the BC manual pages 72 through 74. Back in AB calculus, we spent a great deal of time discussing straight line motion. We had problems that began, a particle travels along the x-axis and has a position of x of t equals t squared minus 4t plus 5. Now we are going to discuss motion along curve paths. As an object moves along a curve in the plane, the coordinates of x and y of its center of mass are both functions of time t. We'll no longer use f and g to represent these functions. We write them as x of t and y of t, which are parametric equations. So we are given an object moving along a curve in the plane where x of t and y of t are twice differentiable functions of t. We describe the object's position or path at any time t as r of t, which is x of t I plus y of t j. Therefore, its velocity is v of t, which is r prime of t, which is x prime of t I plus y prime of t j. We talk about the object's acceleration, which is a vector a of t, which is v prime of t, which is r double prime of t, which is x double prime of t I plus y double prime of t j. The object's speed at any time t is the magnitude of the velocity vector, which is the square root of x prime of t squared plus y prime of t squared. And finally, we can calculate the object's distance traveled between two times t1 and t2 as the integral from t1 to t2 of the square root of x prime of t squared plus y prime of t squared dt. Let's see how these are used in problems. In number 1, you are told that a particle moves along the plane curve described by r of t equals 3 sine of t over 2i plus 3 cosine of t over 2j. And we're asked to find out all aspects of this vector-valued function. In part A, we would like to get a sense of the path of the particle's motion. We can do this in a variety of ways, but the easiest way is to generate a rectangular equation that will describe the motion. So x is equal to 3 sine of t over 2, and that means sine of t over 2 equals x over 3. And y is equal to 3 cosine of t over 2, so cosine of t over 2 is equal to y over 3. So x squared over 9 is equal to sine squared of t over 2, and y squared over 9 is equal to cosine squared of t over 2. Therefore, sine squared of t over 2 plus cosine squared of t over 2 is equal to x squared over 9 plus y squared over 9. And since sine squared plus cosine squared of any angle is equal to 1, our equation is x squared over 9 plus y squared over 9 is equal to 1. And we get x squared plus 9y squared is equal to 9, which we know is a circle. Let us do part C first. We know that our graph is a circle centered at the origin with radius 3, but we do not know its orientation. The best way is to throw in some values of t. When t is 0, we are at the point 0, 3, and when t equals pi, we are at the point 3, 0. So our motion is in a clockwise direction. Next, we are asked to find the velocity vector, the acceleration vector, and speed, and we are to interpret the speed as well. So the velocity vector v of t equals 3/2 cosine t over 2I minus 3/2 sine t over 2j, while the acceleration vector is negative 3/4 sine of t over 2I minus 3/4 cosine t over 2j. The speed will be the square root of 9/4 cosine squared of t over 2 plus 9/4 sine squared t over 2, which is exactly equal to 9/4 times cosine squared plus sine squared, which is 1, and the square root of 9/4 is 3/2. So as our particle moves around the circle, the speed is constant. We are not speeding up, we're not slowing down. D asked us to find the velocity and acceleration at t is equal to pi. First, let's find out where we are. At t equals pi, r of pi is 3 sine pi over 2I plus 3 cosine pi over 2j, which is the point 30. V of pi is 3/2 cosine pi over 2I minus 3/2 sine pi over 2j, which is the vector 0, negative 3/2. And a of pi is equal to negative 3/4 sine pi over 2I minus 3/4 cosine pi over 2j, which is the vector negative 3/4, 0. We place these two vectors on our diagram at the point 30. Our v of pi in blue downward and our a of pi to the left in green. So when we reach the point 30, we have a force going downward, but an acceleration to the left. So if you were on a merry-go-round or any other type of carnival ride that traveled in a circle, when you reach the point 30, your velocity would be going downward, but your acceleration would be traveling inward. These are two competing forces, and that is why sometimes we feel sick when we are on one of these rides. On number 2, you are given the vector-valued function r of t is equal to t squared minus 3I plus tj. You are first asked to sketch the path of the object moving along that curve, and then find the velocity and acceleration functions and determine them at t equals 0 and t is equal to 3. This is a plot of the path. You could sketch it on your calculator in parametric mode or simply plot points. V of t equals 2ti plus j, while a of t is 2I. So v of 0 is simply j, while a of 0 is 2I. V of 2 is 4i plus j, while a of 2 is still 2I. In order to plot our vectors, we need to have locations. So r of 0 is negative 3, 0, and r of 2 is 1, 2. At t equals 0, our particle has a rather weak velocity, straight up, but influenced by a stronger acceleration to the right. So it is no surprise that it is pushed along the blue curve. At t equals 2, the particle has a much stronger velocity because of the acceleration acting on it. There is still an upward component to it, but it is mostly to the right. And since the acceleration is always 2I, it is constant. This would be the likely result of a swimmer trying to cross a river with a strong flowing current. Number 3 gives the vector-valued function r of t is equal to e to the t squared I plus natural log of tj. Because the numbers are not integers, it is suggested that you graph this on your calculator for several seconds to get the path. And then we will find the velocity and acceleration vectors at t is equal to 1 and sketch them on the graph, as well as the speed at t equals 1. We also want to explain what happens to the position, velocity, and acceleration as t approaches infinity. When t equals 0, the plot of our vector-valued function shows that our particle approaches negative infinity. So the plot comes up almost vertically and then makes a very hard turn to the right after it crosses the x-axis. Our velocity function will be 2t e to the t squared I plus 1 over tj, while our acceleration vector will be 4t squared plus 2 e to the t squared I minus 1 over t squared j. So at t equals 1, our velocity is 2ei plus j, while our acceleration at t equals 1 is 6ei minus j. And to find the location at t equals 1, r of 1 is equal to e0. Our speed is the square root of 4t squared e to the 2t squared plus 1 over t squared. So our speed, unlike the last problem, depends upon t. And at t equals 1, the speed will be the square root of 4e squared plus 1. Finally, the limit of r of t as t approaches infinity is infinity, infinity, which means that as t approaches infinity, the further to the right our particle will be and the further up our particle will be. As t approaches infinity, our velocity will be infinity I, which means that as t gets larger and larger, our velocity will be greater and greater, all to the right. While the limit as t approaches infinity of a of t is also infinity I, which means that the particle will have a greater and greater acceleration to the right. At t equals 1, the particle has a strong velocity to the northeast, but a much stronger acceleration to the southeast. So it is no wonder that the particle will still travel to the east, but not gain much height as the acceleration is pushing it south. As time goes by, the j component becomes negligible to the motion, and the velocity and acceleration will just about be all to the east. So the particle's velocity will always be increasing and just about all to the east. In numbers 4 and 5, we work backwards. Rather than starting with the vector-valued functions that describe the particle's position, we now start with a vector value function representing its acceleration and try to determine where the particle will be after a certain amount of time. In number 4, we are told that a particle starts at rest from the point -1, 2, with an acceleration vector of a of t equals I plus 2j, and we would like to find the location of the particle at t equals 2. Since we are given the acceleration, we integrate to find the velocity. The velocity will be the integral of I plus 2j dt, which is ti plus 2tj plus c1. V of 0, therefore, is 0i plus 0j plus c1, and it's because the particle is at rest at t equals 0, that will have to equal 0i plus 0j, meaning that c1 is equal to 0, and therefore our velocity vector is ti plus 2tj. We now integrate to get our position s. So s of t equals the integral of ti plus 2tj dt, which is t squared over 2I plus t squared j plus c2. Plugging in 0, we get 0I plus 0j plus c2 has to equal our particle initial position, which is negative I plus 2j. So therefore, s of t is equal to t squared I over 2 plus t squared j minus I plus 2j. And that is equal to t squared over 2 minus 1I plus t squared plus 2j. So now plugging in 2, we get I plus 6j, or the point 1/6. In 5, we are told that a particle with initial velocity I minus j and initial position 1, 1 has an acceleration vector a of t equals negative cosine ti plus sine tj, and we want to find its position at t equals pi. We start by finding the velocity function. This is the integral of the acceleration function, which is the integral of negative cosine ti plus sine tj dt, which is equal to negative sine ti minus cosine tj plus c1. Plugging in 0, we get 0I minus j plus c1 is equal to the initial velocity, which is I minus j, and that makes c1 equal to I. So our velocity function is 1 minus sine t I minus cosine t j. Next, we find the position function by integrating the velocity function, which is the integral of 1 minus sine t I minus cosine t j dt. And that is t plus cosine t I minus sine t j plus c2. We then plug in 0 and we get I minus 0j plus c2 is equal to our initial position, which is I plus j, making c2 equal to j. So s of t is equal to t plus cosine t I plus 1 minus sine t j. And now plugging in pi, we get pi minus 1 I plus j, or the point pi minus 1, 1. Back in AB calculus, we studied vertical straight line motion involving gravity. If v0 represents the velocity in feet per second of some particle with initial height s0, then the height, which was s, is equal to negative 16t squared plus v0t plus s0, where t is measured in seconds. There was also a corresponding formula if we were working in meters per second. So to find the maximum height, we found s when v, which was ds dt, was equal to 0. And to find the velocity when the particle impacted the ground, we found v when s was equal to 0. Let v0 represent the initial velocity in feet per second and angle theta of an object subjected to gravity whose initial position s0 is x0, y0. Then our path, which we will call r of t, is equal to x of ti plus y of tj, where x of t is equal to v sub 0 cosine theta plus x sub 0, and y of t is equal to v sub 0 sine theta plus y sub 0 minus 16t squared, which is the gravity component. When doing problems with curved motion, where gravity is involved, there are usually three questions that are asked. First, the object's maximum height. To do this, we set y prime equal to 0, and then evaluate y of t at that value of t. If we would like to find the horizontal range, which is how far the object travels in the horizontal direction, we set y of t equal to 0 to find when the object hits the ground, and then evaluate x of t at that value of t. And to find the total arc length between t1 and t2, we integrate from t1 to t2 of the square root of x prime of t squared plus y prime of t squared dt. Number 6 reads, a baseball is hit 4 feet above the ground and leaves the bat at a speed of 105 feet per second at an angle of 40 degrees to the ground. Let's model that. There are 4 questions we need to have answered. First of all, we need a vector function that describes the situation. B, we need a maximum height of the ball. C, we would like to know whether the ball will clear a 12-foot fence that is 325 feet from home plate. And we'd also like to know how far the ball actually travels in terms of arc length. We first want the vector function that describes this situation. S of 0 is 0, 4, assuming that home plate is the point 0, 0. So r of t is equal to x of t I plus y of t j, which is 105t cosine 40 degrees I plus the quantity 105t sine 40 degrees minus 16t squared plus 4j. You might want to put this into your calculator in parametric form and graph this in the window shown for t running from approximately 0 to 8 seconds, and see if you get the graph that you see on the screen. Next, we want the maximum height of the ball. So we take the y component and take its derivative and set it equal to 0. So 105 sine of 40 degrees minus 32t equals 0. And using our calculator, we get t is equal to 2.109 seconds. So we then find the height, which is again the y component at 2.109, and we get 75.176 feet, which corresponds to the graph. Part C asks, will the ball clear a 12-foot fence 325 feet from the home plate? It is really asking whether it is a home run. You can see by the picture it is very, very close. In order to do this, we need to know the value of t when the ball is 325 feet from home plate. So we set our x component equal to 325. 105 t cosine 40 degrees equals 325. Solving for t, we get t is equal to 4.041 seconds. We then find the height of the ball at 4.041, and we get 15.463 feet. So the ball clears the fence by about 3.5 feet. Question D asks, how far does the ball travel? Normally, in a baseball sense, when we ask that question, we want to know how far a home run is hit in the horizontal direction. Here we're asking for the arc length. So the first thing we need to do is to set the y component, 105t sine 40 degrees minus 16t squared plus 4, and set that equal to 0. In order to do that, you're going to have to graph that expression and find out where it crosses the x-axis. It happens when t is equal to 4.277 seconds. So therefore, S is equal to the integral from 0 to 4.277 of the square root of x prime of t squared, which is 105 cosine 40 degrees squared, plus y prime of t squared, which is 105 sine 40 degrees minus 32t, quantity squared dt, which is 381.905 feet. Number 7 reads, water from a fire hose is discharged at a maximum rate of 80 feet per second. Firefighters can get 25 feet from a burning building. They shoot water from their hose at an angle of 45 degrees to the ground. There are two things we'd like to know. We'd like to know the maximum height of the water and how far into the wreckage the water can reach. We first write a vector-valued function to describe the situation. R of t equals x of ti plus y of tj. We assume that the firefighters are shooting the water from a hose from ground level. And therefore, our equation is R of t equals 80t cosine 45 degrees I plus quantity 80t sine 45 degrees minus 16t squared j. We see the graph and it appears symmetric because of the 45-degree angle. To find the maximum height of water, we set the derivative of the y component equal to 0. 80 sine 45 degrees minus 32 is equal to 0. Getting t is equal to 1.768 seconds, and then plug that back into the y component, 80t sine 45 minus 16t squared, to get exactly 50 feet. Part B states that the closest that the firefighters can get to the building is 25 feet. We would like to know how far into the wreckage the water can reach. To do this, we find out when the water level will be back at ground zero, and therefore we set the y component equal to 0. 80t sine 45 degrees minus 16t squared is equal to 0. And therefore t is equal to 80 sine 45 degrees over 16, which is 3.535 seconds. That is double the amount of time it took for the water to reach its maximum height because of the symmetry. We then take that value of 3.535 and plug it into the x component, getting 80 times 3.535 cosine 45 degrees, and we get exactly 200 feet. So the water can reach 200 feet. However, the firefighters are 25 feet from the building, so the water can reach 175 feet into the wreckage. In order to better explain problem number 8 coming up, here is some extra material. A typical golfer generates a club speed of 100 miles per hour at impact. Depending on the club used, the angle will change. Here are graphs depicting ball flights for angles 15 degrees, 30 degrees, 45 degrees, 60 degrees, and 75 degrees. Everything is measured in yards. We assume that there is no rollout. Although it appears that a ball struck at 15 degrees and 75 degrees would travel the same distance, on a real golf course, the ball struck at 15 degrees would roll much further than that of 75 degrees. That is why golfers use clubs with large angles close to the green so the ball will stop quicker. You can see that if there is no change of elevation and no wind, the angle to get the maximum ball flight is 45 degrees. This in itself is a good calculus problem which you can prove. Number 8 reads, a projectile is fired from ground level at an angle of 10 degrees with the horizontal. Find the minimum velocity necessary if the projectile is to have a range of 100 feet. From the golf example previously, we realized that firing a projectile at an angle of 10 degrees will mean that it will not go very far. The only way to make it go further is to change the initial velocity. We are interested in that actual velocity needed to make the projectile travel 100 feet. You see by the graph, we showed three different initial velocities: 50 feet per second in red, 75 feet per second in green, and 100 feet per second in blue. It is clear that the blue example will go further than 100 feet. So we know that our answer is somewhat less than 100 feet per second. But since we wanted to go exactly 100 feet, we need to get the exact value of v. Since we do not know our initial velocity, we will set up our vector valued function as r of t equals vt cosine 10 degrees I plus vt sine 10 degrees minus 16t squared j. For our projectile to travel exactly 100 feet, two things must be true. First of all, the y component must be 0, and the x component must be 100. So we set vt sine 10 degrees minus 16t squared is equal to 0, getting v equals 16t over sine 10 degrees. And we set our x component, vt cosine 10 degrees, equal to 100, meaning that v is equal to 100 over t cosine 10 degrees. Since these are both equal to v, we can set them equal to each other, and we end up with 16t squared cosine 10 degrees is equal to 100 sine 10 degrees. T is equal to the square root of 100 sine 10 degrees over 16 cosine 10 degrees, which gives a value of t is equal to 1.05 seconds. So plugging that into our v formula, for either one, we get 16 times 1.05 over sine of 10 degrees, getting v is equal to 96.727 feet per second. And that seems to go hand in hand with our graph.